Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you close your eyes and, try to picture the ultimate space getaway, you might imagine staring out the reinforced window of a spacecraft, just watching this beautiful, pristine world slowly drifting past you.
Absolutely, that classic sci-fi view.
Right. And I really want to paint that picture for you today because back in February of 1974, humanity actually got a view of something that looked exactly like that.
Yeah, the Mariner 10 flyby.
Exactly, NASA's Mariner 10 spacecraft.
Yeah.
It was hurtling through the inner solar system, and as it performed this flyby of Venus, the cameras snapped this incredibly striking series of photographs.
They're iconic images, really.
They are, and when you look at those archival images, the planet just looks entirely peaceful. I mean, it's just this perfectly smooth, featureless, pearly white orb just hanging there in the pitch blackness of space.
It looks completely harmless.
Right. There are no jagged craters visible, no raging storms tearing across the surface, no harsh colors. It just looks like a giant, pristine marble. Serene, quiet, completely undisturbed.
It really is a stunning piece of cosmic imagery. But it is also one of the greatest deceptions in our entire solar system.
The ultimate catfish.
Yeah, exactly. We are so conditioned as humans to look at a smooth, white, cloudy surface and associate it with calm, maybe a soft winter day or a gentle fog.
Right, it looks like a cloud you could just bounce on.
But what Mariner 10 actually captured was, it's essentially planetary scale camouflage. Because right beneath those tranquil, pearly white clouds is an environment so hostile, so thoroughly apocalyptic, that it is quite literally the closest thing to hell we have ever discovered in our cosmic neighborhood.
Wow. And I think we need to completely shatter that peaceful illusion right out of the gate, because the reality of what is happening under that pristine veil is almost, it's hard to comprehend.
It defies everyday logic, honestly.
It really does. Like
Wow.
if you were to somehow drop down beneath that pearly white exterior in a protective suit and try to just stand on the surface, you wouldn't be standing at all. You'd be instantaneously crushed.
Oh, completely flattened.
Yeah, because the atmospheric pressure down there is 92 times greater than what we experience standing at sea level here on Earth. 92 times.
To put the sheer physics of that into perspective, experiencing 92 bars of atmospheric pressure is the equivalent of being nearly a kilometer or so, about 3,000 feet underwater in Earth's oceans.
Wait, 3,000 feet deep?
Yeah. If you think about the kind of heavy, incredibly reinforced titanium submersibles we have to build just to survive at those depths, that is the baseline environment on the surface of Venus.
That is terrifying. Just standing there is like being at the bottom of the ocean.
And it gets stranger, actually, because the atmosphere at the surface is so dense that it doesn't even behave like a normal gas anymore. It exists as what physicists call a supercritical fluid.
Okay, wait, a supercritical fluid. That sounds like something out of a sci-fi reactor core. How does an entire atmosphere become supercritical?
It's wild, right? It happens when you have carbon dioxide, which makes up about 96% of Venus's atmosphere, and it gets subjected to extreme pressure and extreme heat simultaneously.
So it's basically being squeezed and baked at the same time.
Exactly. It passes the specific critical point where the distinct boundary between a liquid and a gas just entirely disappears. So you aren't walking through a heavy breeze down there.
What are you walking through then?
You'd be wading through this thick, soupy, viscous fluid that constantly surrounds and crushes everything it touches. I mean, it flows like a gas, but it has the dissolving power and the density of a liquid.
That is deeply, deeply unsettling. You're wading through a glowing, crushing soup. And we haven't even brought up the temperature yet.
Oh, right. The heat is a whole other nightmare.
Yeah, the surface of Venus sits at a staggering 467 degrees Celsius. That's 873 degrees Fahrenheit.
Which is hotter than the surface of Mercury, by the way, even though Mercury is much closer to the sun.
Right. And just to give a practical reference for that kind of heat for you listening, if you took a solid block of lead or zinc or tin and just set it on the ground on Venus, it would instantly melt into a puddle.
It would just liquefy.
Just liquefy. And to put the final terrifying touch on this whole environment, those serene clouds we talked about from the Mariner 10 photos, the ones that look like a soft winter fog.
Yeah, definitely not water vapor.
No, they are made of concentrated sulfuric acid.
And that acid cycle is particularly vicious too. It actually rains sulfuric acid high up in the atmosphere, but the surface is so unimaginably hot that the acid rain boils and evaporates miles before it ever even hits the ground.
So it's just this permanent, hovering acid mist.
Exactly. It forms a permanent corrosive haze. It is a world that seems actively designed to destroy anything that comes near it, which, makes the underlying reality of Venus so bewildering for planetary scientists.
Because it shouldn't be like this, right?
No, not at all. By almost every metric we have, Venus shouldn't be a hellscape. It should be Earth's twin.
That's the part that really boggles the mind. If you look at the raw stats, Earth and Venus are practically identical. I mean,
Yeah.
they're roughly the same size. They have almost the same mass. They have similar gravity.
They're virtually the same age, too.
Right. They're located in the same general neighborhood of the inner solar system, and they formed at the exact same time out of the exact same primordial dust and gas.
If you were an alien astronomer looking at our solar system from, say, 1,000 light years away, you would see two blue-green, habitable-looking planets right next to each other. You would assume they evolved identically.
So how do you start with two identical twins made of the same stuff at the same time and end up with one being this vibrant blue marble teeming with oceans and forests, and the other being a toxic, crushing 873-degree supercritical inferno?
That divergence is basically the holy grail of planetary science.
I bet it's the ultimate what went wrong scenario.
Exactly. And the general consensus is that you won't find the answer by looking at anything happening on Venus today. The surface has been completely scrubbed. To figure out what went so disastrously wrong, we have to look incredibly far back in time.
Like to the very beginning of the solar system.
Yeah, we have to rewind the clock roughly 4.5 billion years to the very chaotic, incredibly violent first 50 million years of our solar system's existence.
Because the evidence points to a single cataclysmic event, doesn't it?
It does. It points to something massive.
We're talking about a massive moon-sized object acting as a cosmic wrecking ball. An event so violently profound that it permanently altered the planet's fundamental mechanics.
Yeah, it fundamentally broke the planet.
But to even begin to understand how we know this ancient catastrophe happened, we have to look at the strange, perplexing way Venus moves through space today.
Right, because planetary movement is essentially a massive historical record. The mechanics of how a planet spins, its tilt, its orbital speed, these aren't just random numbers that it was born with.
They're like scars.
Exactly. They are the cumulative physical result of everything that has ever happened to that body, and Venus moves in a way that defies almost everything we expect from a rocky planet.
Let's get into the kinematics, the study of its motion, because the numbers for Venus are just absurd. I mean, on Earth, we are entirely used to our rapid counterclockwise rotation.
Sure, our standard 24-hour day.
Right. We spin on our axis once every 24 hours. It's a brisk pace. It keeps the weather systems churning. It gives us our standard day and night cycle. But Venus, on the other hand, is moving at a pace so sluggish it almost seems broken.
It's barely moving at all, rotationally speaking. And its sluggishness is really only half the anomaly. The truly baffling part is that it is spinning in the wrong direction entirely.
The retrograde spin.
Yes.
So Earth, Mars, Jupiter, almost everything in our solar system spins counterclockwise. But Venus spins clockwise.
It's the odd one out.
And it does it so agonizingly slowly that a single rotation on its axis, so one single Venusian day, takes 248 Earth days to complete.
Just let that number sink in for a second. 248 Earth days.
It's wild.
In the time it takes Venus to spin around just one single time, Earth has gone through winter, spring, summer, and fall. In fact, Venus's day is actually longer than its year.
Wait, its day is longer than its year?
Yeah. It orbits the sun in 225 Earth days, but it takes 248 days to spin on its axis once.
That is just... It breaks my brain a little bit. If I'm trying to visualize what that practically means for the surface, assuming you could survive the pressure and the heat, and you could somehow see through the thick sulfuric acid clouds, what would a day even look like?
Well, the sun would slowly rise in the west because of the backward spin.
Right, the west.
And it would take more than 100 Earth days just to cross the sky before finally setting in the east. The sheer length of the days and nights is terrifying.
So you're just sitting under the blazing sun for over 3 months straight.
Yes. It creates a thermal dynamic that is profoundly alien. Because when a planet spins that slowly, the side facing the sun is subjected to a relentless, unending bombardment of solar radiation for months on end.
So all that heat just bakes into the atmosphere in one spot.
Exactly. Meanwhile, the dark side is plunged into an equally long, stagnant night. You completely lose all the rapid atmospheric mixing and the daily thermal relief that a fast-spinning planet like Earth enjoys.
Man, if you're trying to picture how anomalous this backward spin really is,
Yeah.
think of Earth like a beautifully balanced spinning top.
I like that analogy.
Yeah, so you pull the string, it hits the table, and it's just humming along, spinning rapidly and smoothly in a nice counterclockwise direction. It has all this wonderful, stable momentum.
It's happy.
Right, it's happy. But Venus looks like a spinning top that was violently kicked, like something hit it with such immense force that it completely killed its natural forward momentum, stopped it dead, and left it slowly, drunkenly spinning in the opposite direction.
That visual is remarkably accurate to the physics involved, actually. And the reason planetary scientists have been so obsessed with this retrograde anomaly for decades is that planets do not just spontaneously decide to hit the brakes and reverse course.
Because of the laws of physics, right?
Right. The laws of physics strictly forbid it.
Why is that exactly? What dictates the default spin of a planet in the first place? Why counterclockwise?
It all comes back to how a solar system forms. If you picture a giant, formless cloud of cold gas and dust floating in space, eventually gravity causes this cloud to collapse in on itself.
Okay, so it starts squishing together.
Right. And as it collapses, it starts to spin. And just like an ice skater pulling their arms in during a spin, the more it collapses, the faster it spins, eventually flattening out into a massive swirling disk. We call that the protoplanetary disk.
Like a giant cosmic pizza dough.
Yes, exactly. The star forms in the center, and the planets form from the leftover dust swirling around it in the disk.
So because the entire massive dust cloud was already spinning in one direction, let's say counterclockwise, everything that forms out of that dust should also be spinning counterclockwise.
Precisely. It is called the conservation of angular momentum. The planets are basically inheriting the spin of the original dust cloud.
They don't have a choice.
No choice at all. So, for a planet the size and mass of Venus to completely violate that inherited momentum, to just stop and spin backward, an external force of unimaginable power must have intervened. It is literally the only way the math works.
You need a massive energetic event to essentially grab the planet and physically force it into reverse.
You do.
Which is where the work of Cedric Gilman and his team at ETH Zurich comes in. They are planetary scientists who recently presented some really groundbreaking models at the European Geosciences Union General Assembly. And they basically took on the task of figuring out exactly what kind of force it takes to stop a world.
And their approach to solving this mystery is fascinating because they essentially had to treat the solar system like a 4.5 billion-year-old crime scene.
Right, you can't just go dust for prints.
Exactly. They couldn't just guess what happened. They had to work backward. They started with the slow rotating observation, so the 248-day backward crawl we see today, and they fed that endpoint into highly advanced computer simulations.
So they're reverse engineering the apocalypse.
Yeah, they used these models to test millions of permutations, just trying to find the exact initial conditions that could produce the Venus we see now.
They're essentially running the physics engine of the universe in reverse. They're asking, what happens when you throw a ridiculously large rock at another ridiculously large rock?
And not just any rock. The simulations revealed that to alter the momentum of a planet that massive, you need an impactor roughly 1/10 the mass of Venus itself.
1/10 of the entire planet's mass. To give that some scale for you listening, we aren't talking about a standard asteroid here. We aren't talking about the 6-mile-wide meteor that wiped out the dinosaurs.
No, that would barely be a scratch.
Right. An object that is 1/10 the mass of Earth, or Venus, is roughly the size of our moon. You have a solid, rocky, fully formed planetary body, thousands of miles across, hurtling through the dark void of the early solar system.
It is a terrifying amount of mass.
Just a rogue moon on a collision course.
Exactly. But the models showed that the mass alone wasn't enough to solve the mystery. The geometry of the collision was absolutely critical because if that moon-sized object had struck Venus dead center like a perfect bullseye, it wouldn't have caused the retrograde spin.
Wait, really? Why not? Wouldn't a direct hit transfer the most energy?
Well, it transfers the most energy into the core, yes. If you have a dead center impact, the kinetic energy goes straight inward, driving a massive shock wave through the center of the planet.
Okay.
But it doesn't give you leverage. If you want to change how a massive sphere spins, you need torque. You need to hit it on the edge. So the models concluded that the impactor had to strike Venus at a very high angle. It had to be a tangential, off-center, grazing blow.
So instead of a head-on car crash, it's more like a sideswipe, but at tens of thousands of miles per hour?
Precisely. That glancing blow acts like a giant cosmic hand.
It grabs the edge of the rapidly spinning planet and violently wrenches it the other way.
Yes. The models show that this specific type of tangential strike could take a young, healthy, rapidly spinning Venus, slam the brakes on its rotation, and induce a faster backward spin.
And then over time, it slowed down.
Exactly. Over billions of years of gravitational friction, that initial backward spin slowly decayed into the sluggish 248-day crawl we see today.
Okay, but I'm struggling with the mechanics of survivability here. Because if an object the size of the moon, traveling at 30 or 40 kilometers a second, slams into a planet, wouldn't the planet just cease to exist?
You'd think so, right?
I mean, how does a rocky sphere take a punch of that magnitude and not just shatter into a billion pieces of gravel floating in orbit, like the Death Star exploding or something?
It's a completely natural question, because our daily intuition tells us that a high-speed collision of that size should be totally destructive. But this is where planetary physics really diverges from our everyday experience.
How so?
It all comes down to a concept called gravitational binding energy. When a planet gets to be the size of Venus, its gravity is so intensely powerful that it holds its own mass together with incredible force.
So it's basically squeezing itself into a ball.
Yes. To permanently shatter a planet that big, to actually blast its pieces so far apart that they don't just immediately fall back together, requires an energy threshold that is truly astronomical, much more than even a moon-sized impactor can deliver.
So even if it fractures into pieces, the gravity just pulls all the pieces right back into a sphere.
Exactly. But furthermore, the tangential angle we talked about actually saves the planet from total obliteration.
Oh, because it wasn't a dead center hit.
Right. In a head-on collision, all that energy plunges directly into the core, which can literally unbind the planet and blow it apart. But with a high-angle grazing blow, a vast amount of the impactor's kinetic energy is spent on friction, on shearing off the outer layers, and on altering the angular momentum.
So it bleeds off the energy on the surface.
Exactly. The impactor itself might be completely vaporized and its material merged with the planet's outer crust, but the host planet's core remains intact. It survives structurally.
That paints just a wild picture. The planet takes the hit, the moon-sized rock is pulverized and absorbed into the crust, and Venus remains a single, intact sphere.
Battered, but intact.
But, just because it stayed in one piece doesn't mean it walked away unharmed. Surviving the kinetic impact was just the beginning, because the physical consequences on the interior of the planet were apocalyptic.
Beyond apocalyptic, really. Because when an object that large strikes a planet, the laws of thermodynamics take over immediately.
Right, the energy has to go somewhere.
Exactly. You have a staggering amount of kinetic energy, the sheer motion of a moon-sized rock traveling at cosmic speeds. That energy cannot just vanish when the rock stops. It has to convert into another form. And in a high-speed planetary collision, kinetic energy instantly converts into heat.
And we are not talking about a modest heat wave here.
Not at all.
We are talking about the surface of the planet literally melting into a global ocean of glowing rock. The simulations dive deep into the immediate aftermath of this collision, and depending on the exact speed and angle, the heat transformation is unimaginable.
The models run a whole spectrum of scenarios. On the mild end of the collision parameters, if you can even call it mild, you still get a shallow melt layer covering the entire globe, maybe 100 kilometers thick.
Wait, 100 kilometers?
Yeah, so that is 62 miles deep of pure, sloshing liquid magma coating every single inch of the planet.
62 miles deep of lava is the mild scenario.
Right. That's if it barely clips it. The extreme scenario, which the researchers note is highly likely given the immense energy required to actually reverse the planet's rotation, is that the kinetic heat transfer melted 99% of Venus's mantle.
99%.
Yes.
The mantle being, for context, the vast rocky interior of the planet that sits right between the dense iron core in the center and the thin outer crust on the surface. It is the bulk of the planet's volume.
It's almost the entire planet.
And the models suggest that 99% of that solid rock was instantly turned into a liquid. The entire planet essentially became a giant droplet of glowing, molten magma floating in space.
It's an event of such violence that it resets the entire geological clock of the world.
Wow.
But here is where the story takes a fascinating and, frankly, incredibly frustrating turn for scientists. You would assume that an event that violently melts an entire planet would leave behind some obvious, glaring physical scar.
Yeah, a crater the size of a continent, or a weird wobble, or a massive dent.
Something, right? A strange density anomaly, something we could point our instruments at today and say, there it is, there's the proof of the impact.
Right, if you hit a planet with the moon, there should be a bruise. But there isn't. And that leads to a really profound observation about how planets actually cool down in the vacuum of space.
It's all about insulation, or rather the complete lack of it. When a planet has a solid rocky crust, like Earth does, that crust acts like a heavy blanket.
It keeps the heat in.
Exactly. It traps the internal heat of the core and mantle inside the planet, and that heat escapes very slowly over billions of years through volcanoes and tectonic vents. But when you melt 99% of the mantle, you destroy the crust entirely. The blanket is gone.
It's just ripped away.
Yep. You just have raw liquid magma directly exposed to the freezing vacuum of space.
And liquid magma is incredibly efficient at radiating heat away, isn't it?
Extremely efficient. Without a solid crust to trap the energy, the heat from that unimaginable collision just vents directly out into the void. Because the heat transfer is so efficient, a global magma ocean actually cools down and solidifies back into rock remarkably quickly on a geological timescale.
How quickly are we talking?
We're talking maybe a few 100 million years, which is a blink of an eye in the life of a solar system.
Wow. So the rock cools, it solidifies, it forms a completely new crust.
Yeah.
And as the models point out, once that heat is efficiently radiated away and the magma turns back into a solid surface, the thermal signature of the planet looks exactly like a planet that was never hit at all.
It normalizes completely.
That is so wild.
Yeah, the heat is gone, the rock is solid, the planet settles back into a perfect sphere, and to any telescope or probe, it looks thermally completely standard.
It is the ultimate cosmic cover-up, like a perfect crime.
Yeah.
I was thinking about this, and if you imagine someone has an incredibly detailed, beautifully carved ice sculpture.
Okay, an ice sculpture.
Right, and it has all these intricate ridges and cuts, which represent the craters and the early geological history of a young planet. Now, someone comes along and hits that sculpture with an industrial blowtorch until it melts entirely into a puddle of water.
Right, it's just gone.
Then they take that water, pour it into a smooth spherical mold, and freeze it back into a standard block of ice.
That's a great analogy. All the physical evidence of the original trauma, all the unique carving marks, the impact points, they are completely erased by the melting and refreezing process. You are left with a pristine, smooth block of ice.
Exactly. A detective examining that ice later would have absolutely no way of knowing what the original sculpture looked like or that a blowtorch was ever used. The melting process covers the tracks perfectly.
It really does.
But even though the obvious physical bruise healed and the heat dissipated, the mechanical damage was done. The planet was now spinning at a drastically reduced backward speed. And that one mechanical change triggered a terrifying cascade of consequences for the planet's climate.
This is where we bring in the insights of planetary astrophysicists, particularly people like Stephen Kane, who have dedicated their research to understanding the profound connection between a planet's rotation and its ability to harbor life.
And it's a connection we often overlook, honestly.
It really is. When we talk about finding life in the universe, we always focus on the presence of liquid water or the distance from a star. We never really think about the spin rate as a vital ingredient for habitability.
Why is rotation so critical? Why does the spin matter so much for the climate?
Because rotation dictates how a planet manages its energy. A planet is constantly receiving massive amounts of heat from its star. If it wants to maintain a stable climate, it has to have a mechanism to redistribute that heat.
Okay, so it has to move the heat around.
Exactly. On Earth, our rapid 24-hour rotation acts like a massive atmospheric whisk. It drives the Coriolis effect. It creates vast weather systems that constantly churn the atmosphere, moving intense heat away from the equator toward the freezing poles and dragging cool air back.
So it's a constant global mixing system.
Right. It prevents any one side of the Earth from baking excessively while the other side freezes solid. The energy is spread out evenly, but when you violently slow that spin down to a 248-day crawl, that rapid mixing engine just breaks down entirely.
Stops.
The heat stops moving efficiently. You have one side of the planet staring directly into the intense radiation of the sun for months on end. The solar energy hits the atmosphere and just pools there, creating immense stagnant zones of thermal radiation.
And that completely messes up the weather.
Oh, completely. That lack of rotation fundamentally alters the way clouds can form and circulate.
because you don't get the protective, swirling storm systems that can reflect solar radiation back into space. The energy just gets trapped.
Right.
But the slow rotation is really only the first domino in this climate catastrophe, because the impact that stopped the spin and melted the mantle likely had a devastating effect on Venus's geology, too specifically, its plate tectonics.
Yes, and this is a crucial piece of the puzzle. Now, it's important to note that scientists are still heavily debating the exact mechanism by which the impact halted Venus's tectonics.
There are a few theories, right?
Yeah. Some believe the magma ocean depleted the crust of water, making it too dry and rigid to slide around. Others think the extreme surface heat prevented the crust from cooling enough to become dense, which is needed to subduct back into the mantle.
But regardless of the exact mechanism, the end result is the same.
Exactly. The undeniable reality we see today is that Venus has absolutely no plate tectonics. Its entire surface is a single, unbroken, stagnant lid of rock.
And a stagnant lid is a death sentence for a planet's climate. Because without plate tectonics, you lose the planet's most important recycling system.
Specifically, carbon recycling. This is the mechanism that keeps Earth habitable today. Earth actually has a massive amount of carbon, just like Venus does.
But on Earth, it doesn't all sit in the atmosphere.
Right. Our plate tectonics act as a giant planetary thermostat.
How does that thermostat actually work? Like, how does shifting rock control the atmosphere?
It's a really beautiful cycle, honestly. Carbon dioxide in Earth's atmosphere dissolves into rainwater. That slightly acidic rain falls onto rocks, weathering them, and washes carbon-rich minerals down into the rivers and eventually into the oceans.
Okay, so the carbon washes into the sea.
Yep. And in the oceans, marine organisms use it to build shells, or it just precipitates out naturally and settles on the ocean floor as limestone. Eventually, because Earth has shifting tectonic plates, that ocean floor is dragged down, subducted deep into the Earth's mantle, locking the carbon away safely inside the planet.
It literally buries it.
It does. Volcanoes will eventually release some of it back out, but the cycle keeps the overall atmospheric levels completely balanced.
It's this elegant, self-regulating loop. But on Venus, that loop was completely severed. Because the crust is a single, solid, stagnant lid, there are no shifting plates. There is no subduction, which means there is nowhere for the carbon to go.
Exactly. Venus still had active volcanoes constantly pumping carbon dioxide out of the interior, but with the recycling system broken, that carbon just built up in the atmosphere century after century, millennium after millennium.
And carbon dioxide is greenhouse gas. It is incredibly efficient at letting sunlight in, but preventing the resulting heat from radiating back out into space.
It acts exactly like a greenhouse.
So you enter this terrifying feedback loop known as the runaway greenhouse effect. The volcanoes pump out carbon, the carbon traps the heat, the planet gets hotter, the heat bakes the surface, perhaps releasing even more trapped gases.
It's a vicious cycle.
And because there is no tectonic recycling, the carbon just keeps piling up, thickening the atmosphere, trapping exponentially more heat. Over millions of years, this runaway train compounds until you arrive at the monstrous environment we see today. An atmosphere so incredibly dense with trapped carbon that the pressure crushes you, and the trapped heat skyrockets to an ambient 467 degrees Celsius.
And as if a broken carbon cycle and a stagnant, backward-spinning atmosphere weren't enough, Venus was also fighting a losing battle against the sun itself.
Right, because of its location in the inner solar system. Venus is significantly closer to the sun than Earth is. And the sun isn't just a static light bulb, it is an evolving star, which guarantees a brutally difficult timeline for any planet in its inner orbit.
Stellar evolution is a relentless force. Our sun is a main sequence star, and as it ages and burns through its hydrogen fuel, its core actually becomes denser and hotter. As a result, the sun steadily increases in luminosity.
It gets brighter.
Yeah, it gets roughly 10% brighter and hotter every billion years.
10% every billion years. So even if Venus had somehow miraculously managed to maintain a stable climate early on, even if it had struggled through the impact and kept a fragile balance, the relentless assault of an ever-brightening sun was constantly turning up the dial on the heat.
Exactly. You combine an aging, brightening star with a stagnant atmosphere that can't recycle carbon, and a runaway greenhouse becomes completely inevitable.
It's a total convergence of catastrophes. But all of these cascading failures, the slow rotation, the stagnant lid, the runaway greenhouse, they all trace back to the changes induced by that initial primeval impact. Which brings up a profoundly tragic scientific question.
The big what if.
Yes, the what if that keeps planetary scientists awake at night. Because Stephen Kane and others have pointed out that rotation rate is key to habitability. If the backward, 248-day crawl was caused by an impact? Is it possible that before the moon-sized rock smashed into it, Venus was spinning normally?
It's highly likely.
And if it was spinning normally, was it actually a paradise?
It is a deeply haunting possibility, and the models completely support it. If we look at the initial conditions of the solar system, before all the chaotic impacts altered their paths, Venus very likely had a rapid forward rotation.
Just like Earth.
Just like Earth. It likely had a functioning climate system. It is entirely scientifically plausible that early Venus had vast oceans of liquid water, a stable, breathable atmosphere, and conditions that were perfectly suitable for the emergence of life.
Wow. It completely reframes how we view the planet. That impact 4.5 billion years ago wouldn't have just been a neat geological event where rocks smashed together. It would have been the ultimate sudden extinction event, the instant erasure of a fully habitable, thriving twin Earth.
It really is chilling to think about, that a world right next door could have been a vibrant paradise, and it was essentially murdered by a random, chaotic strike from the dark.
It highlights the extreme fragility of planetary evolution. And this tantalizing ghost of a past habitable Venus leads directly into the final, lingering mystery that scientists are currently agonizing over today. It is a puzzle locked deep inside the planet's core.
Yes, going back to the models developed by the team at ETH Zurich, they have managed to model the mass of the impactor, the angle of the strike, the depth of the magma ocean, but there is one major unresolved variable in their equations.
A question that completely alters how we view the planet's history.
Exactly, and it all comes down to water. The question is the interior of Venus still wet?
It sounds like a simple binary question, but the implications of the answer are staggering. Let's look at the two divergent realities here. First, the dry scenario. If the deep interior of Venus is completely dry today, then the story makes logical sense, right?
Neat and tidy, yeah.
It means that the violent impact, the 99% mantle melt, and the subsequent runaway greenhouse effect successfully baked every single drop of moisture out of the planet. Venus lost all its water to the vacuum of space, and it is a dead, desiccated rock all the way down to its iron core.
It's a tragic story, but a closed book.
But the alternative scenario, the wet scenario, is where the physics get incredibly complicated and incredibly exciting. What if, despite the cataclysm, despite the magma oceans, there is still a massive reservoir of water locked deep inside the interior of the planet?
Which is what Cedric Gilman considers the most perplexing unanswered question today.
I have to admit, I have a really hard time visualizing how that is even physically possible. Let's just review the timeline we just established. A moon-sized object hits the planet at thousands of miles an hour. The sheer kinetic energy instantly liquefies 99% of the rocky mantle. You now have a global ocean of glowing, liquid rock that is directly exposed to the freezing vacuum of space, radiating intense heat. If there was any water in that rock, wouldn't it instantly boil, turn into vapor, and vent off into the void? How in the universe could water possibly survive inside a molten planet?
It seems utterly counterintuitive, I agree. If you boil a pot of water on a stove, the water evaporates. So a boiling planet should lose its water. But we have to fundamentally redefine what wet means in a geological sense.
Okay, so we're not talking about puddles.
No, we aren't talking about subterranean lakes of liquid water splashing around in caverns. We are talking about water molecules, hydrogen and oxygen, that are chemically bound within the actual crystalline lattice of the rock itself.
So the water is physically part of the mineral structure.
Correct. Minerals deep in a planet's mantle, like ringwoodite or wadsleyite, can absorb water like a sponge, trapping it within their chemical bonds.
Oh.
Now, when the impact melted the mantle, you are right, a massive amount of those bonds would break, and the water would violently degas into the atmosphere and escape to space. But the interior of a planet is subjected to crushing, unimaginable pressure from the sheer weight of the rock above it.
So gravity steps in again.
Exactly. The mystery scientists are trying to solve is whether the intense heat of the magma ocean was enough to overcome that confining pressure entirely, or if the sheer crushing weight of the deep interior managed to hold on to some of those chemical bonds, keeping the deepest layers of rock chemically wet.
So even when it turns to liquid magma, the pressure thousands of miles down might be so intense that it forces the water to stay trapped inside the melt.
That's the theory. And then, when the magma cools and solidifies back into that perfect crime block of ice we talked about, the water is still locked inside the solid minerals.
Precisely. And if the interior is indeed still wet, it means our fundamental understanding of how planets survive apocalyptic trauma is incomplete. It means a planet can take a direct hit from a moon, melt entirely, and still harbor the essential ingredients for life deep within its mantle.
It means Venus might still be holding on to the ghost of its ancient oceans, completely hidden beneath the stagnant crust and the acidic 467-degree surface.
The fact that we have these incredibly advanced supercomputers, and we can model the exact trajectory and kinetic energy of an impactor from 4.5 billion years ago, but we still don't know the answer to this incredibly basic question about whether our closest planetary neighbor is wet or dry on the inside. It just proves how deeply alien Venus truly is.
We've barely scratched the surface, literally and metaphorically.
It is a stark and humbling reminder of the limits of our knowledge. It shows us just how effectively a single chaotic event in the infancy of a solar system can permanently obscure a planet's true nature. We look at Venus and see a smooth white cloud, entirely blind to the violent history underneath.
It's the ultimate disguise.
Let's take a step back and just marvel at the staggering sequence of events we've explored today. You start with this peaceful-looking, pearly white orb hanging serenely in space. But beneath that illusion is a toxic, crushing reality of supercritical fluids and melting lead.
Right.
And we've traced that nightmare all the way back to a single moment of cosmic violence. A rock, a tenth the mass of the planet, comes hurling through the dark and strikes a grazing blow. That one tangential hit transfers enough rotational torque to violently stop a rapidly spinning world in its tracks and throw it backward into a sluggish 248-day crawl.
And the sheer energy of that hit melts 99% of the solid planet into a glowing magma ocean. The molten surface destroys the crust, effectively halting the tectonic mechanisms needed to recycle carbon.
So the thermostat breaks.
Right. With the thermostat broken, the atmosphere chokes on carbon dioxide, setting off a runaway greenhouse effect that, combined with the relentless heat of an aging sun, bakes the world completely beyond recognition.
And the cruelest part is that as the magma ocean rapidly cools in the vacuum of space, all physical evidence of the impact is seamlessly erased, leaving behind only the mechanical scars of a backward spin and a silent, stagnant crust.
It is a terrifying chain reaction on a planetary scale, a paradise murdered by a random rock.
And I really want to leave you with a chilling perspective to mull over. Right now, humanity is constantly looking up at the night sky, peering through our most advanced telescopes, scanning the galaxy for Earth-like exoplanets.
We're obsessed with finding them.
We are. We find these distant worlds, and we get incredibly excited, classifying them as habitable, based primarily on two main factors: their size and their distance from their host star. If they sit in that perfect sweet spot, the Goldilocks zone, where water could theoretically pool on the surface, we assume they might be teeming with life.
But we have to remember, Venus is in that exact sweet spot. Venus is Earth's twin in size and distance.
Exactly. Venus checks all the boxes on our habitability checklist. If the tragic history of Venus teaches us anything, it's that habitability is not just about real estate. It is not just about being the right size at the right distance.
Location isn't everything.
If a single, random, grazing cosmic collision billions of years ago is the only difference between Earth's vibrant oceans and Venus's toxic, supercritical hellscape, we have to ask ourselves a very dark question. How many of those incredibly promising Earth-like exoplanets we are discovering out there in the deep galaxy are actually just dead, backward-spinning infernos hiding behind serene, pearly white clouds?
It completely reframes our entire search for life in the universe. It serves as a stark reminder that surviving the chaotic, rock-strewn environment of a young solar system isn't just about physics. It is a terrifying game of cosmic roulette.
It really is. The margin for error is basically non-existent. The next time you see a picture of Venus or spot it shining brightly in the evening sky, take a moment to remember the apocalyptic history hiding beneath that beautiful camouflage. Thank you so much for joining us on this journey today. We appreciate you taking the time to explore the mysteries of our solar system with us. Keep looking up, keep asking questions, and we'll catch you on the next one.